Okay, let me know if you cannot see this, and we'll get started. We're going to look at simulations and applications in probability. We'll look at simulations in probability, we'll look at odds, and then something called expected value. Okay, a simulation is a technique used to act out a problem by conducting experiments whose outcomes are analogous to the original problem. And that just means that they are very similar to the original problem. Using simulations, students typically estimate a probability using many trials rather than determining the probabilities theoretically. So sometimes we will use something called a random digits table. This table is generated by a computer or a calculator. So obviously if you, this is not like a set table, this is just one example of one, but if you were to have your calculator generate one or a computer, the digits might look differently. Okay, but a lot of times we'll use this to simulate what the problem is asking for. Okay. So for example, let's say we needed to simulate a coin toss. So maybe you don't have a coin toss, or you don't want to take the time of tossing it 100 times or 50 times or whatever. What you can do is pick a number at random to start and then read across the table. You'll let an even digit represent heads and an odd digit represent tails. So you don't have to start at the beginning of the table. You just pick somewhere to randomly start. So maybe I'll start here where it says 96377. And so basically I would write down as I'm going through the digits there. We said even is heads and odd is tails. So I would write down, if I'm starting with this 9, I would say tails, head, tails, 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 heads, tails, tails, heads, tails. Count a 0 as an even, so that would be heads, heads, and so on. And you would just go through the table and call off heads or tails however many times you want to represent the simulation. In this example, we have a baseball player that has a batting average of 400. This gives his experimental probability of getting a hit on any particular time at bat. We want to estimate the probability that he will get at least one hit in his next 3 times at bat if the at-bats are independent events. So we can use a random digit table there rather than having Reggie come up and hit 3 times. And so basically, since his batting average is 400, then you're going to say the 0, 1, 2, and 3 represents a hit, and then 4 through 9 would represent not a hit. Okay, so we're using 0, 1, 2, 3 because his batting average is 400. So we'll use 4 digits to represent a hit, and then the remaining digits to represent, the other 6 digits represent not getting a hit. So here's a random digit table, and if we are using that, basically we've gone through and all of the digits that are 0, 1, 2, and 3 are in red. The other digits are in black, so you can see the simulation using this table. Okay, so if I were to count up how many red digits I have, there are 42, and that's out of the 50 trials. So we would estimate his probability for getting a hit as 42 out of 50, which would be 0.84. Okay, this is one for you to try. So those of you who are watching the video later, pause the video and see if you can work through the problem, and then we'll look at the answers together. Okay. So we're going to use, it says to use a random digit table or the stat crunch. We're going to just use this random digit table that I copied from the previous slide. We want to use that to estimate the probability of the event that a couple that determines to have 3 children will have 2 girls and 1 boy. And then on B, we'll determine the theoretical probability of the event. And then on C, discuss whether or not the answers are the same. Okay, when you do this, it's going to vary. It's going to depend on your random digit table. Even if you're using the one that I'm given, it will depend on where you start. So I just pick one. I counted girls as even and boys as odds, and then I picked a number and went through and started saying, okay, the 9 represents boys, so boy, girl, boy, 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 girl, boy, and so on. And I just went through however many. When I did it, I ended up with 3/5 when I just used 5 trials, but then when I went through 16 digits, I ended up with 6/16, which gives me 3/8. Okay, so it'll just depend on what number you decide to start with, and then just record from there. Okay, for theoretical probability, you'll just, if you want to have 2 girls and 1 boy, you're going to make a tree diagram from that. And so basically you're going to have, you're going to work that out, and you'll end up with 3/8. So you will make either a tree diagram, or if you'd rather make a table, you can do that. And as you can see, you won't necessarily end up with the same answer. I happen to when I tried more trials, but the more times you do an experiment, the more likely you're going to get to the theoretical probability. So when I ended up with 3/5, I was off for sure. And then once I ended up using 16 trials, I got closer. So it will not always result in the same probability. But once again, once you repeat it a larger number of times, then it should start to get closer. Okay, computing odds. We're going to let the probability of A be the probability that A occurs. And when you have A with a little bar over top of it, that means the complement, or in this case, it would be the probability that A does not occur. Then the odds in favor of an event would be the probability of A over the probability of A complement. Okay, and we talked last week about how to find the complement, we just take 1 minus the probability of A. And so here's another way to write the formula. So these formulas here in the box would be something I would write down. Those are going to be formulas you're going to use in this section. When you want the probability that the odds are against an event, then you're basically just going to flip that fraction. You're going to take the probability of the complement over the probability of A. And that's how you compute odds. So when you have equally likely outcomes, the odds in favor will be the number of favorable outcomes over the number of unfavorable outcomes. The odds against would be that flipped, the number of unfavorable outcomes over the number of favorable outcomes. So that basically means the same thing as what we had on the other slide. But if you like it written out in words instead of that mathematical notation, there it is there. So whichever way is easier for you to know those formulas, that would be something I would write down. Okay, so on this, let's look at how to use the formula. So we want to find the odds in favor of a given event. So on A, we want to roll a number less than 5 on a die. So there are 4 numbers less than 5. There are 2 numbers that are not less than 5. So it would be 4 to 2. That reduces to 2 to 1. Now, this time they're putting it with the colon, but that means the same thing as 4 over 2, which would reduce to 2 over 1. Okay. So just watch on MyLab what notation they'll want you to have. So you can list probabilities as fractions, you can list them with the colon, or you can even divide the fraction out and list it as a decimal. Just pay attention to how MyLab will want you to write it. Okay, on B, the probability of tossing a heads on a fair coin, that's going to be 1 to 1 because there's on a coin, there is a head, so that's the 1, and there's a tails, so that's the other one. Any questions on that one? Okay, continuing on, let's find the odds in favor of drawing an ace from an ordinary 52 card deck. So, how many aces are in a deck of cards?
It's 4, right?
Right, so 4. So that gives us our first number, and then the other number will be how many cards are left. So if we have 52 cards and 4 of them are aces, that leaves us with 48 cards. So it's going to be 4 to 48. That reduces to 1 to 12. Okay, and even though you're not writing this as a fraction, you can still use your calculator to reduce the fraction if you need to. Let me pull that up here. Okay, so if you struggle reducing fractions, you're going to do this on your calculator. Alpha y equals number 1 will help you let you put in a fraction, and you're going to type in the 4 on top, 48 on the bottom, and it reduces it to 1 to 12. Okay, drawing a heart from an ordinary 52 deck card. That should give us basically the same result as what we had on C because there's 4 aces. That means there's 4 of every type. So there's, mixing those up. I'm thinking the ace is the number this time. With the heart, you've got 4 different suits in a deck of cards. So that means there's 13 hearts. If I take 13 from 52, that's 39, and 13 to 39 is your odds, which would be 1 to 3 because it reduces. I guess I was thinking ace and spade. I don't know. Okay, this one is one for you to try. So take a second to see if you can work through this, and then we'll go over it together. So those of you watching the recording, pause the video, and then we'll come back. Okay, so for this one, if we are looking at a die and we have 1 through 6 dots, that means we want to look at the numbers 1 through 6 and figure out how many numbers are prime. So we've got the number 1, that's prime. 2 is prime. 3 is prime. 4 is not, so we'll skip 4. 5 is prime. 6 is not. So that gives us 4 different prime numbers, leaving 2 that are not prime. So we're going to say 4 to 2, which reduces to 2 to 1. Any questions there? Okay, computing odds. If the odds in favor of an event E are M to N, then the probability of E would be M over M plus N for the odds in favor. For odds against, then you're going to say the probability of E would be N over M plus N. Okay. So take a second to write those down. Okay, and the difference in this and what we did before is this is actually, instead of just counting the odds, we're figuring out the probability of it happening. Okay, so for this one, if the odds in favor of achieving a Grand Slam golf sweep are 2 to 9, what's the probability of the event of achieving the sweep? So if you're achieving it, that's going to be our odds in favor. So when I have M to N, I take M over M plus N. So in this case, my M is 2. So I'm going to say 2 over and then 9 plus 2. So 2 to 11. Okay, and then the last thing we're going to look at is something called expected value. If in an experiment, the possible outcomes are the numbers a sub 1, a sub 2, all the way up to a sub n, and they have the probabilities p sub 1, p sub 2, all the way up to p sub n, then the expected value E is given by this formula. Now, that looks a lot more complicated than it actually is. So let's look at an example. And then if you want to come back to the slide to write down the formula to make sure you understand what it means, you can. But I think once you see it, you'll be worked out. You'll be fine. Expected value can be used to predict the average result of an experiment when it's repeated many times. It cannot be used to determine the outcome of any single experiment. And it's considered a fair game when payoffs are involved and the net winnings are $0. So the expected value minus the cost to play a game of chance. Then when that happens, then we call it a fair game. So if you pay $10 to play the game, and then you end up winning $10, then that you break even. Okay, so when the expected value minus the cost is 0, then that's considered a fair game. Okay, so in this example, it costs you $5 to play a game when 2 coins are tossed. You receive $10 if 2 heads occur, $5 if exactly 1 head occurs, and nothing if no heads appear. Is this a fair game? So when we're looking at this, the probability or when you toss 2 coins, you can have a heads and a head. That probability would be 1/4. Okay. You can get a heads and a tails or a tails and a head. That would be a half, and the probability of 2 tails would be 1/4. So that's from what we learned last week. If you were to make a chart, these are basically the 4 outcomes you can have when you toss 2 coins. You can toss and end up with 2 heads. You can end up with a heads and a tails and a head, which would basically be the same thing. So that's why that's a half, and then you could also toss 2 tails. So there's 4 possible outcomes. 1 that's heads, 1 that's tails, and if you count these as the same, that gives you 2 out of 4, which reduces to a half. Okay, so you're going to take each of these probabilities and multiply them by the amount that you receive from this second sentence here, and then we'll calculate out the winnings. Okay. So for heads, that's a fourth, and we said that you receive $10 if you toss 2 heads. So 1/4 times 10. Okay. Then for the second part, the probability of a heads and 1 heads and 1 tails is a half. Well, you end up getting $5 if that happens. So you're going to add 1/2 times 5. And then if you, there's a 1/4 chance that you'll toss a tails. And if you toss 2 tails, then you end up with nothing because you have nothing if no heads appears. So 1/4 times 0. So if you multiply this out on your calculator, 1/4 times 10 plus 1/2 times 5 plus 1/4 times 0, you end up with $5. Okay. So if you win $5 and you paid $5 to play the game, then that was a fair game because your net winnings are 0. And that is it.